Got burning questions? We've got some cool answers. In this video, we outline the basics of heat transfer, with a view on real-world applications, ranging from chemical processing, the nuclear industry, power generation, clinker production for cement, semiconductor doping, pharmaceuticals, and, last but not least, food processing. But, before anything else, what are the principles governing heat transfer? Let's set the stage for heat transfer, linking it to thermodynamics. Thermodynamics is the big picture boss, dictating how much energy shifts as heat or work. It's all about energy swapping outfits. Now, don't worry about the pentagram-shaped diagram here. It's not a summoning circle for confused students, though it may feel like that when thermodynamics starts waving its magic wand. Such visuals help untangle the chaos of energy transformations. Take gravitational potential energy, GPE, kinetic energy, and internal energy. They are all shapeshifters, converting from one form to another. Thermodynamics sets the stage with initial and final energy states, but it's heat transfer that fills in the details of the journey between them. Heat transfer is a so-called rate process. Think of a falling object. The rate of change of gravitational potential energy matters. Similarly, in heat transfer, we're focused on the rate of change of internal energy. Thermodynamics tells us why heat moves and by how much, while heat transfer asks, how fast. This distinction is crucial for designing heat exchangers, insulators, and thermal management systems. Thermodynamically, the driving force for rate processes is a potential difference. This concept is illustrated using energy level diagrams. In the gravity example, the variation in gravitational potential is represented by a change in height. For heat transfer, the equivalent driving force is a temperature difference between 2 points. Having outlined the fundamentals, we'll now clarify some common misconceptions. Here's an air conditioning system, with the heat flow extracted from the room into the unit. The heat from the room is then released by the outdoor unit to the exterior environment. Here's also an example of a heat pump, which is an AC system in reverse. In this case, heat is extracted from the exterior environment, which is then transferred into the room. But, how is this physically possible, and what's going on? What are the hidden mechanisms? Let's explore further. Back to the heat pump. Now we show the work input, given by the blue arrow. And, the same applies to the air conditioning unit too. Let's consider these two systems, focusing on the air conditioning unit. An energy diagram shows heat flowing from the cold interior to the hot exterior. This process defies nature's preference, requiring work to drive it. Normally, without work, heat flows from hot to cold, as thermodynamics dictates. Understanding this helps clarify how air conditioners manipulate energy to keep us cool, using work to reverse natural heat flow. Now, let's unpack the AC system for clarification. It's a refrigeration cycle with two closed loops, divided by an expansion valve and a compressor that does the work. From left to right, heat appears to flow from the cold evaporator coil to the hot condenser coil. But, zoom in onto a single coil, and heat flows naturally from the warmer tube wall to the colder surroundings, aligning with thermodynamics. The study of heat transfer focuses on this type of spontaneous process. A fridge also showcases these principles. Internal energy is pulled from inside the fridge and dumped into the room, depicted by the curved arrow for heat flow. Meanwhile, heat sneaks back into the fridge through its walls, following natural heat transfer. This illustrates how refrigeration moves energy against its natural direction, using work, while heat transfer describes the spontaneous leakage back into the system. Focusing on leakage across the fridge wall, we see a temperature gradient through its cross-section, marked by a delta-T difference. Heat flows down this gradient, like a river carrying internal energy through the material. Simply put, heat transfer, Q dot, is the movement of this internal energy, flowing naturally from warmer to cooler areas, driving the process we observe. Now we've seen how energy flows against natural gradients using work, let's explore a common everyday mystery: why do some objects feel colder than others? Consider this: If you touch a cushion, it feels warmish. If you then touch a metal object, it feels a lot cooler. So, what is the physics responsible for this phenomenon? We call upon our gravitational analogy here again, with our falling object over a distance delta h. We previously alluded to rate processes, here represented by the rate of loss of gravitational potential energy, E dot. Assuming the object falls at constant velocity. E dot is given by mg delta h over delta t. Roughly speaking, this can be recast by the following ratio. Here, such a ratio can be generalized as a rate being proportional to the driving force divided by the resistance. In the analogy here, the driving force can be envisaged as the gravitational potential, and a measure of resistance as the inverse of the observed mass transfer rate. I have boxed this last equation, being important, as it's universally applicable to many areas of physics, such as heat transfer, fluid mechanics, mass transfer, and electrical circuits, etc. So, how does this framework help us account for why certain objects feel colder to the touch? Okay. Back to heat transfer. We have two energy levels, shown here as hot and cold. Think of each energy level representing a hot and cold region within an object, separated by a temperature difference of delta T. Using the generalized relation of driving force divided by resistance, we can express the heat flow as delta T divided by 1 over K, where K is the thermal conductivity of the material the object is made from. Thinking back to the cushion and metal ornament. Both objects there are at room temperature, say 22 Celsius, but your hand has a temperature of about 30 Celsius. Delta T corresponds to a hand-to-object difference of 8 Celsius here, but the thermal conductivity of the metal is significantly higher than the cushion. On a relative basis, the metal with its higher K value has a corresponding lower resistance to heat flow. What you experience on touching is an enhanced heat flow from your hand, thereby the metal object is perceived to be cooler, despite being at an identical temperature to the cushion. Okay, so much for rate of heat flows. Let's now address the three ways of how heat can be transported from one object to another. The first is conduction. This occurs primarily in solids, but also, to a lesser extent, in fluids. The second is convection. This only occurs in fluids, that is, liquids and gases, and not forgetting supercritical fluids too. The third is thermal radiation. This does not require a medium to transport the heat from one object to another. Together, these mechanisms form the holy trinity of heat transfer. Finally, let's bring together the how fast, expressed as rates, with the how, the underlying mechanisms, to formulate the quantitative laws governing each mode of heat transfer. We will start with conduction first. Using a simple example of a slab made from a single material of thermal conductivity, K, and dimensions of area A, and thickness delta X. In this case, a temperature gradient is imposed through the slab in the X direction. This results in an absolute difference, delta T, and consequently, a heat flow through area A, in the X direction. Using the general rate relation from before, we note heat flow is proportional to the temperature difference and the conductivity. We also need to account for the effect of area. Normalizing the heat flow by the area over which it flows results in a quantity called flux, little q dot. The slab thickness must be accounted for, also, since the resistance to heat flow is proportional to delta X. Taking these together, we finally come to a more general result, highlighted here. This is known as Fourier's law, founded by Joseph Fourier in 1822. Noting that the negative sign here accounts for heat flowing down the temperature gradient. In this fundamental form, the temperature variation is considered only in the X direction. Now, to convection. This involves bulk movement of fluids, being primarily responsible for heat transport in this case. Consider a solid object with its exposed surface in contact with a fluid. If the fluid's bulk temperature is lower than the surface temperature, we observe a declining temperature profile through the fluid. This drives heat flow from the solid object into the fluid. It is instructive to note that, for the case of conduction, temperature profiles are generally curved. However, we saw in our last example for conduction that temperature profiles can be linear in their simplest form. For convection, temperature profiles are always nonlinear, that is, curved, even in the simplest of cases. This reflects the differing nature of convection from conduction. Using the general rate relation, we note that heat flux is proportional to the temperature difference and the heat transfer coefficient, H. Remembering flux is defined as the absolute heat flow normalized by the surface area. Taking these together, we finally come to a more general result, known as Newton's law of cooling, founded in 1707. Note, this deceptively simple relationship comprises the heat transfer coefficient, which is a constant of proportionality, and can be determined empirically. Furthermore, the temperature difference adopts a positive value in the case of cooling an object, and negative values for the object being warmed by the fluid. In the latter case, the fluid's temperature profile would be inverted. And, finally, we consider thermal radiation as the third mode of heat transfer. Thermal radiation is typically introduced later in undergraduate courses and often covered only briefly. It involves emission and absorption of electromagnetic radiation from objects, by virtue of its temperature. Such radiation is chiefly composed of infrared wavelengths, you know the type you feel when you place your hand underneath the grill in the kitchen. Now, imagine two parallel plates facing each other, where temperature T1 is hotter than temperature T2. What actually happens is a continuous exchange of thermal radiation between the two surfaces. The thermal radiation emitted from surface 1 occurs in all directions. Surface 2 then absorbs the thermal radiation emitted from surface 1. And surface 1 absorbs the radiation emitted back from surface 2. Note how the arrow magnitudes indicate the relative intensity of the radiation, increasing with hotter temperature. Since T1 is larger than T2 here, the overall net exchange of radiation is from surface 1 to surface 2, as shown. Here, we consider an idealized case where the two surfaces are in full view of each other, that is, they are mutually visible with no obstructions. This means all radiation emitted from surface 1 strikes surface 2, and is not lost to the surroundings in the process. The same logic applies in the reverse direction. Such an assumption is achieved using two large parallel plates, and helps to simplify the maths. We also assume the surfaces possess an emissivity, epsilon1 and epsilon2, close to a value of 1. This is termed as black surfaces, being close to ideal emitters and absorbers. We finally come to a more general result, known as the Stefan-Boltzmann law, founded in 1879. Here, sigma is a universal physical constant, known as the Stefan-Boltzmann constant. Note, this is a basic formulation for the net radiative heat transfer from object 1 to 2. Temperatures T1 and T2 must be expressed in Kelvin to ensure correct application of the fourth power relationship. Due to this strong temperature dependence, radiative heat transfer becomes practically significant only at elevated temperatures, typically above 500 Kelvin, as a rule of thumb. We also observe that no medium is needed for heat exchange to occur, and therefore no temperature profile exists between the two boundaries, unlike the previous examples of conduction and convection. Some important points need to be addressed, for the simplified Stefan-Boltzmann law to hold. First, thermal radiation is primarily a surface phenomenon in engineering applications, as emission and absorption occurs at the surface, not within the bulk. The Stefan-Boltzmann law therefore applies to surface temperatures only. Most solids are opaque, meaning only their surfaces participate in radiative heat transfer. However, materials like glass can be semi-transparent, allowing radiation to pass through. In such cases, a surface coating can be used to render the material opaque. Such tailored coatings can significantly alter the surface properties, enhancing or suppressing heat transfer without needing to replace the entire object. This ability to tune emissivity is a unique and practical aspect of radiative heat transfer. Second, for the interlayer between the surfaces, the opposite applies. The Stefan-Boltzmann law is exactly valid in the case of a vacuum, or non-absorbing medium that is fully transparent to thermal radiation. This includes certain gases, liquids, or solids that do not participate in emission or absorption. Approximate non-participating media include dry air, mineral oil, and quartz glass, under appropriate conditions. So, in conclusion, all of these foundational laws for conduction, convection, and radiation enable engineers to predict and control energy flows across countless systems. Whether it's cooling a reactor, generating electricity, or doping semiconductors, mastering heat transfer begins here. If you enjoyed this video, you may want to check out this one covering similar themes. Thank you for watching. Bye for now.